So, welcome to this class on hardware security. So, we shall continue our discussions on power attacks and power analysis. So, we were discussing in the last class on difference of mean attacks. So, we shall be discussing about how to implement difference of mean technique on simulated traces. We shall be discussing about a new technique next, about which is called as correlation power attacks or CPA, and we shall also be discussing about how to implement CPA on simulated traces. So, this is a brief recapitulation of what we already discussed. So, essentially how difference of mean works is essentially the basic principle of, it's basically based on the principle that in DOM, right, we try to kind of exploit the fact that power consumption of a device is correlated to a target bit or set of bits, and the attacker essentially obtains a large number of power consumption curves and corresponding ciphertext. It can also be done from the plain texts, but suppose it is done from the ciphertext, which is probably more I would say intuitive, and then the attacker basically applies a divide and conquer strategy. So, he assumes a portion of the key which is required to perform the decryption for a portion of the cipher of one round, say the last round for example. So, he basically guesses a part of he basically sees the ciphertext, guesses a part of the key and does say one round of decryption, and then based upon the guessed key he computes a target bit. So, typically this is after computing an inverse S box. Like suppose I want to calculate the input of the last round S box, I need to perform an inverse S box on the exclusive OR of the portion of the ciphertext and and the portion of the key which you are guessing, and because you do not know what is the key, so you guess that byte of the key for example, and then you calculate the inverse S box, and then you basically find out any, or you target some specific bit. So, this could be for example the LSB that you target, it could also be the MSB, or it could be any linear combination of the bits also. So, depending upon whether the target bit is 0 or 1, and that depends upon your guess of the key, the traces are divided into a 0 bin and a 1 bin, okay, and it is expected that for the correct key, or correct key means the portion of the correct key, the difference of mean would be non-negligible for a specific time instance which is say T star, okay, that is T star is the time when actually the computation is taking place, okay, is essentially happening. So, therefore, right, I mean because like sometimes when you are starting to work on or DPA for example, it probably is a good idea to kind of start with something which are called as simulated power traces. So, you basically try to simulate the power trace and develop your technique. Later on, right, you can of course replace the simulated power traces by the real power traces, in which case the attack will become more difficult because you will be having noise and other phenomenon. But to develop your technique and to understand your technique, right, simulated power traces is a good starting point. So, let us start with that, like with such kind of power traces which we will be simulating. So, suppose let us consider a rolled AES architecture. A rolled AES architecture, as we have seen, means that there is one round of AES and you are basically kind of iterating it to get all the 10 rounds of AES. So, it is basically an iterated architecture, and you basically what you are trying to do is you are basically trying to kind of calculate the power consumption of this device, okay. So, now of course, like when you are actually doing this attack, you will be having the actual setup and hence you will be getting it, but what we will be trying to do is in this, or considering in this case, is we will be trying to get a simulation or simulated power trace. So, let us see how we can do that. So, so what I mean to say is essentially this, like now you have this rolled architecture, which means you have your AES block, this is your AES round, and the AES round, the output of the AES round, suppose you are storing in essentially a register. This register S essentially is storing the corresponding result of your encryption, okay. So, basically like this is not the complete AES. So, this is just say one round of AES and it is being iterated. So, I am not drawing a very accurate diagram, but this is kind of indicative, that is initially you basically take in the plain text, and of course, like there is a key that you need to kind of XOR, okay, and you start your operation of AES and of AES round, and then every clock cycle that you do, like essentially you know that there are 10 rounds of AES operations. So basically you are essentially latching some data onto this register, okay, and because of the dynamic switchings which are happening in this register, you are expending power, the architecture is consuming power, right. So therefore you can imagine that this state register, I mean although this is very hypothetical figure, essentially, right, it is basically consuming power in 12 distinct time instances, okay. The first time it is expending power is when you are doing the initial add round key, okay, that is you are doing the initial add round key operation. At that point it is expending a power, and then there are 10 rounds of AES operation, okay, and finally you are getting the ciphertext, okay. So typically, right, that is essentially your 1 plus 10 plus 1. So there are 12 time instances or 12 instances in time when the register essentially is making a toggle, and therefore there is a power which is being consumed. So what we basically try to model in our simulated environment is we basically see the register content, and suppose you have a very simple model like Hamming weight or Hamming distance. Based upon that you kind of predict the power consumption, okay. Note that when you are doing this prediction, you have a 128 bit register. So you are basically considering the 128 bit register, and based upon that, right, you know that the Hamming weight, for example, could be from 0 to 128. So there could be like 129 possible power levels, and therefore, right, depending upon the content of that register, content of the 128 bit state register, you kind of indicate a power consumption. You say that my AES for this particular time instance is consuming such amount of power, okay. So this is again a simulation, and we essentially try to use this simulated framework to develop our technique or experiment on our technique, okay. So therefore, right, I mean with this kind of like simulated power trace, we would like to basically now get into how the DOM works, okay. So therefore, right, imagine that I do n sample number of such operations, okay. So n sample typically means that you essentially have like you are basically encrypting plain text, for example. Suppose you are encrypting say like 1000 plain texts. So therefore n sample would denote the number of randomly chosen plain text which you are encrypting, okay. So basically like you are encrypting say n number of inputs, and that n is essentially here n sample, okay. Now in such an architecture, in such a rolled architecture, as I said, a register is updated by the output of the AES round after every encryption, okay. And the power trace is again, so now you are basically storing the power trace, okay, in a register. I mean you are basically storing it in array, okay, and the array name is say sample n sample endpoint, okay. So that means basically, right, essentially it is a 2-dimensional, as you can see, it's a 2-dimensional array. So you can visualize this as that you are basically storing the power in the form of a 2D array, where essentially suppose you are using this index to like say the number of the sample, like suppose you are encrypting the first or the second or the third and so on, and this axis essentially is storing the point or the time instance of your AES operation, okay. So this is your, this direction is your endpoint, okay, and endpoint, as we have seen for our simulated environment, is say 12, because there are 12 time instances when the register is making a toggle. There is an initial add round key followed by the 10 rounds of operation, and finally when you are getting the ciphertext, okay. So for each power trace, we also store the corresponding ciphertext, okay, because we also need the ciphertext, and the ciphertext essentially, as you can understand, is that if there are n sample plain text that you are encrypting, you get n sample ciphertexts, okay, and that is essentially denoted by this array, which is ciphertext n sample, okay. So we simulate the power traces by using the power model. So the power model could be like Hamming weight or Hamming distance on the state of the register before the encryption, okay, and then followed by that of the initial key addition. Then after that there are like 9 rounds of encryption, and finally there is a ciphered state that you are generating, okay. So therefore the endpoint is 12, and we choose n sample something like say 8000, okay. So this is an ad hoc choice, but suppose in like your n sample is 8000, okay. So now okay, so now let me clear this, okay. So now so there is a simple trick that you can observe, that particularly this works when you have your Hamming, your power model is Hamming weight power model. So when the power model is Hamming weight, a single trip can be developed. So let the attack target one of the key bytes. Okay, so let me call that as key, for example. Now therefore you basically target a corresponding S box. So this S box could be, say, the first S box of your last round. So we denote the corresponding ciphertext byte in the array ciphertext n sample as cipher. Okay, so again this is the first byte of your ciphertext. For each of the n sample runs that you are doing, the analysis partitions the traces into 0 bin and 1 bin, and it targets the, it basically depends upon the, depending on the target bit, it partitions into 0 and 1 bin. Now for estimating the target bit, the attacker computes the inverse S box on the XOR of the byte cipher and the guessed key byte, because we know that cipher is your corresponding ciphertext byte and the corresponding key which you are guessing is a key. You XOR them, calculate the inverse S box, find out your target, and you split and you put your trace into either the 0 bin or into the 1 bin. But note a point that the ciphertext for which the ciphertext byte corresponding to a target byte, okay, is a cipher, okay, will map into always the same bin. So what I mean to say is that even if for example, if you consider AES, there are 16 bytes in the cipher. Imagine the 0th byte, for example. Okay, so if the 0th byte is a constant, irrespective of what is the value of the remaining 15 bytes, that power trace will go to either the 0 bin or will go into either the 1 bin. Okay, so that implies that you can basically, like rather than storing the power trace into the array sample n cipher endpoint, which essentially, I mean, rather than storing it into the array that we saw previously, which was sample n sample endpoint, because you had like 8,000 encryptions, you can now store the same information in a smaller array. You can store it in, say, sample n cipher endpoint, okay, and n cipher in our case is something like 256, because that byte can take only 256 values. Okay, so you need not store that in an array. Like sometimes when you are attacking, for example, as we will see, right, countermeasures, you may need millions of traces. Okay, you may need millions of encryption. So you need not have such a big array, but you can actually store that into a much smaller array depending upon the size of your word. Okay, so you can store it in, for example, sample say 256 endpoint. Okay, because what you are basically doing is you are kind of partitioning your entire power trace set into 256 partitions. Okay, and all the members of that partition, whether it will go into the 0 bin or whether it will go into the 1 bin, irrespective of key guess, actually will go into the same bin. Okay, because their fates are same. So therefore, right, you need not store that in such a bigger array. Okay, so this is a simple trick that you can try to adopt when you are developing your implementations. So how do you compute the DOM? So for all the endpoint instances, we simulate the power traces by observing the Hamming weight of the encryption states for all the endpoint instances. Okay, that means endpoint is again 12. So for all these 12 instances, you basically like you can simulate the power traces. So I'm talking about the simulation right now. So you can simulate by observing the Hamming weight of the encryption states for all the endpoint instances, and instead of storing these traces separately, you can combine them by adding those traces corresponding to which the ciphertext byte is a cipher. Okay, so what you can do is, because later on you need to calculate the average, so what you can do is that for all those traces, okay, or for all those corresponding encryptions where the 0th byte, say, takes a specific value, you essentially can just add on to its current content in the array where you are storing the power traces, and you can store the sum. Okay, so you can store the sum, and therefore you can essentially like optimize your storage. And the entire DOM process, therefore, like as we will see, you can actually write that in a very systematic manner in a nice form of an algorithm which you can code and which you can automate. So the algorithm basically splits the traces into 2 bins based on the target bit, say LSB, and then we compute the DOM and store the highest value of the DOM as an array, which is, say, bias key. Okay, so the number of entries in bias key will be how much? Will be again the number of possible key guesses. Okay, and you have got 256 key guesses for, say, the 0th key byte. For every possible guess, you guess a bias. Okay, that bias is nothing but the difference of mean. Okay, and as we have discussed previously, that if you have a correct key guess, then there should be an endpoint, some time instance, when you should get a non-negligible value for the difference of mean. Okay? And if you get a negligible value of difference of mean at all instances, then it is quite likely that that is not your candidate key. Okay? So therefore, the key which has got the highest bias key value should be returned as a possible candidate key. Okay? So therefore, this is essentially the whole idea, and that essentially has been written in the form of an algorithm. Okay? And the algorithm essentially does nothing but essentially does, or like implements whatever we have discussed till now. Okay? So basically, if you read, and this you can read in details from the textbook that we cite, and you will find that what it basically does, it calculates an XOR of the cipher and the key. So the cipher is say the 0th byte and key is say 1 byte of the key. You kind of XOR them, you calculate the inverse S box, okay, and then you basically go to the input of the S box, okay, and then that is what you call as partial cipher. Okay. Then what you do is you extract the LSB of partial cipher. So you do an ANDing with say 1, you can extract any other bit also for that matter, but suppose we extract the LSB, because based on the LSB we will now partition the traces. Okay. And if that bit is say 1, that means if that bit is 1, then what we do is that we start incrementing the counters for the 1 bin. Okay. So we basically have a sum bin, that means the summation of all the power traces for bin 1, we increment that. We also increment a counter, that means how many traces are going into that particular bin. Okay. And note that your sample array is now indexed by cipher, because as I said that you essentially can index it by the 256 values. Okay. And then if that bit is 0, then you do similarly for the 0 bin. So basically you calculate the average, and finally you calculate the difference of the averages, and that is stored in this min diff array, and then you find out the absolute mean. I mean, you find out the like the maximum absolute value, and the idea is that whichever gives you the maximum value is basically returned as the corresponding correct key. So here is an experimental run on this, and you can very well simulate it, because if you have an implementation of AES, even without going to a setup actually, which may be costly and not always reachable, you can actually easily simulate the power traces, and you can try this algorithm. You can just try to maybe implement it using simple C. Okay. So exactly that is being done here. It is basically done on this simulated environment where there is no noise. That means the power essentially is modeled by the Hamming weight of the 120-bit state register. Okay. And then we apply this difference of mean technique, and then we target the last round, that means the 10th round of AES, and we try to do a DPA on say the first key byte. Okay. And as you can see that this shows how the bias value kind of increases for the correct key, whereas it doesn't for the wrong keys, and therefore you can easily distinguish the correct key byte from the wrong key bytes, and therefore it shows that the difference of mean attack works in this setting. More realistic simulation would be where you can add a Gaussian noise to your power model, to your simulation. So you can use any library which generates this kind of noises, and you can kind of embed it or superimpose it on your Hamming weight values. And now if you try to do a difference of mean, as you can see that the attack becomes more difficult, but nevertheless you can see the separation. Okay. So the separation is not as wide as here, but we still get a separation, and we are able to retrieve the correct key. So therefore that brings us to the like the link between difference of mean and power model. As we have discussed priorly also that the power models can be of different types. For example, like Hamming weight, you have got the Hamming distance power model. So the question is, right, how can you adapt your technique for Hamming distance power model? Okay. And if you think right, then it can easily be done so. The only change that you have to do is that now the classification of the power traces would be based on the change of the transitions rather than the absolute Hamming weight. Okay. So you have to basically calculate the Hamming weight, but the Hamming weight will be on the XOR of the present state with the previous state. Okay. So therefore if you again target the last round of AES, then you can see that the state register initially holds the output of the 9th round. Okay. And after the final round, it gets replaced by the 10th round output, which is the cipher. So therefore if you take an XOR between the cipher and the 9th round input, right, I mean the 9th round output, sorry. So if you take an XOR between the cipher and the 9th round output and find out the Hamming weight of that, then essentially you can again do the same thing. Okay. So the rest of the description remains exactly the same. So you can easily adapt your technique and make it work when you are like modeling your power using say a Hamming distance power model. But here is a very key important point. That means Hamming weight and Hamming distance, although we have been using, one of the reasons we are using them is because they are easy to use. Okay. So there is something which is called as stochastic power model, which basically is also or maybe mentioned here. Okay. So the difference of mean technique, as we have seen for DPA, is actually what is called as a non-profile attack. Okay. So non-profile means that the attacker essentially gets the hardware where the secret key is embedded and starts to do the attack right away. Okay. As opposed to this, there is another category of side channel attacks which are called as profile attacks. In profile attacks, one needs to have access to a pair of identical devices. Okay. So there are two identical devices. The first one is a target, which is essentially where you have got limited control and there is a running cipher, say AES, with a fixed key. You cannot change that key. Okay. On the other hand, in a profiling stage or a profiling phase, you have been provided with a similar hardware, exactly identical hardware, where you have full knowledge and you have got control on all the inputs. Like you can change the inputs, you can change the key, and you can do profiling as much as you want. Okay. So profiling can be used to stochastically learn the power model more accurately, and that will probably help you to improve the accuracy of your power attack. Okay. So for example, like if you consider a target byte, say the last round of AES. Okay. So let us write by this equation. What we are trying to do is, so we are trying to say consider x, which is a portion of the cipher, and k or small k as a portion of the key which you are guessing in the last round. And then suppose you basically what you are doing is you are calculating the inverse S box, which is denoted here as S inverse. Okay, so you are calculating S inverse of x XOR with k, and this I denote as say phi of x comma k. Okay, so this phi of x comma k is my deterministic portion of my power consumption. Okay, because it kind of can be determined. It is not a noisy component. It is also called as signal, as we will see later on. Okay. So it is the signal component of your power consumption. So when you calculate this phi of x comma k, what you do is you apply a function subsequent to that, which is say gi or denoted as gi, which does nothing but extract an ith bit. As we have seen in our algorithm, right, we had extracted the LSB. So gi basically tries to extract any one of the bits, say the ith bit of the state phi x comma k. And now you essentially have say a register or a byte, for example, and you want to predict what is the corresponding power consumption because of that content. Okay. So what we were doing previously is that we were tacitly assuming a Hamming weight, for example, right, and Hamming weight would mean that every bit is equally contributing. Okay. But on the other hand, as we know that in an electronic circuit, right, lot of weird things can happen. What can basically happen is that each of the bits are basically contributing in a different manner. Okay. And that essentially is captured by this equation, where we write that the power consumption is modeled as sigma of I equal to 1 to 8, because there are 8 bit positions, and each of these each of the contributions of the bits, or each the way each of the bits are contributing are modeled by this coefficient, say bi. Okay, so you have got b1, b2, b3 and so on till b8, and you also have b0, which basically stores any other component. Okay. So in the profiling phase, we keep the deterministic part defined and we keep it kind of constant by keeping phi of x, we keep the x and k constant, and we essentially try to like observe different power values. Note that because of noise there will be like still subtle differences, and therefore, right, you probably will have like an over-defined system of equations. You probably need an over-defined system of equations to solve the values of these BIs. Okay. So here is an experimental like description written by this paper by Schindler and other co-authors, where they try to develop a stochastic model for differential side channel cryptanalysis. Okay. So you can observe that here there is an experiment which has been done with 4 different keys. Okay, and the deviation of the so here we plot, say the so here is a plot of the 8th coefficient, that is B8 for example, and we show how B8 varies over time. So you can easily see by that by this variation of B8 that if you are applying a Hamming weight power model, then that is not accurate, because in a Hamming weight power model we are assuming that the contribution of any of the bits, right, is kind of constant over all time instances. But you can observe here that that is not so. Okay, and also another interesting point is that even if you are changing the key, the deviation is actually minor. That means there is a small deviation in your prediction of the corresponding contribution. So that implies that like you need not always know the correspondingly correct key. You can very well work with any guess, okay, any guess of the key byte, and that would give you quite a good estimate about what is the contribution of the bits, and therefore you can understand what is the stochastic model of your device, okay. And later on, right, you can for example, in this case, another point to be noted is that here there were 2000 equations which were solved, and therefore, right, you need an over-defined system of equations. But after doing this effort, right, you have got a better understanding about your leakage model, which you can try to exploit in your next phase of the power attack. And that is why, right, these power attacks are very strong, okay. But at the same time, right, you need an access or an opportunity to do this profiling phase, okay. So wherever it is possible, we should do this. Okay, so now we will start discussing about correlation power attacks, or CPA. So I will just initiate this discussion, and we will see more details subsequently. So in a correlation power attack, this is exactly, or quite similar to the difference of mean based attack, because here also you are relying on the fact that you are basically targeting an intermediate computation, and typically the input or output of an S box, just like the DOM technique. These input values are computed from a known value again, which could be like say the ciphertext and a portion of the key which is guessed. And the powered model again, so again you are using a powered model, say again we are using the Hamming weight powered model, and then you are using it subsequently and applying it to develop now a hypothetical power trace, okay. So in the previous case, we were kind of trying to correlate the power trace with a single bit or to a linear combination of bits, okay. But in this attack, we will be trying to kind of develop a hypothetical power trace and try to correlate it with a real power trace, okay. And we have to see how we can develop the data structures and how do we define our correlations to better understand how the attack works, okay. So this we will take up in the next session, and we will continue our discussion, okay. Thank you.